Hey guys, welcome back to another lecture video for Chem 115. In this lecture video, we will learn how to express the equilibrium constant Kc, and we will also learn how to write a mass action expression from a chemical reaction or chemical equation. So let's go ahead and get started. Now in the previous lecture video, we learned about reversible reactions such as this. Also, we learned that a chemical system can achieve a state of dynamic equilibrium if the rate of the forward reaction is equal to the rate of the reverse reaction. And so we are going to be using this definition of equilibrium to help us define the equilibrium constant, which is capital K with a subscript C, or just simply Kc. For us to do so, we're going to go ahead and rely on a concept that we learned in kinetics. If you recall, the rate of the chemical reaction can be defined by its rate law, such that the rate of the chemical reaction is equal to the rate constant K, lowercase k, times this by the concentration of that substance, whatever it is, raised to a specific power. For now, I'm going to call it x. And so if we take the rate of the chemical reaction to represent either the rate of the forward or the rate of the reverse, this allows us to substitute in this term, these two terms, to this specific expression. In other words, the rate of the forward reaction is equal to the rate constant of the forward reaction times that by the concentration of the reactants raised to some power. And this whole term is equal to the rate of the reverse reaction, which can be expanded to the rate constant of the reverse times that by the concentration of products raised to another power. So now that we've expanded on the definition of equilibrium, what we're going to do is we're just going to move all of the concentration terms on one side, and we're going to move all of the rate constant terms to the other side. And to do so, I'm going to go ahead and simply divide the concentration of reactants to the other side, giving me the rate constant K of the forward equals to the rate constant K of the reverse times this by the concentration of products raised to some power. Divide this by the concentration of reactants raised to another power. So now that I have all of my concentration terms on one side, I'm going to go ahead and divide out the rate constant of the reverse. And so what I get is the rate constant of the forward in the numerator, divide that by the rate constant of the reverse in the denominator, and then that's going to equal to the two concentration terms that are raised to their own power. And so it turns out that the ratio of the two rate constants will give us the equilibrium constant Kc. And so here in this case, this K is going to be capitalized. And once again, this Kc, this capital K with a subscript C, is going to represent our equilibrium constant. Okay. And so the equilibrium constant is simply a ratio of the two rate constants, which is the rate constant of the forward divided by the rate constant of the reverse. Okay, and so that's going to give us the equilibrium constant, capital K subscript C. Now, another way to represent the two individual rate constants is by using 1 and -1 that you guys see here. Okay, and so remember that the rate constant of the forward is represented by lowercase k with a positive 1. Divide this by rate constant k, -1. So this is representing the forward, and this is representing the reverse. Okay. All right. So now that we've defined the equilibrium constant, we're going to go ahead and take a step back real quick, and we're going to talk about the mass action expression. And so the mass action expression can be derived from the concentration terms that's left over. And so if a reaction is at equilibrium, then the ratio of products to reactants is what's going to give us the backbone for the mass action expression. Okay. And so let me write that down right here. So this gives us the backbone of the mass action expression, where it's simply a ratio of products over reactants. Now, for a more complicated chemical reaction, remember that there are coefficients typically in front of the chemical formula. And so to take into consideration the stoichiometry of a balanced chemical reaction, we're going to go ahead and use those coefficients as the superscript in a mass action expression. And so notice that little d right here, little d, little e, little f, and little g, they are going to be the coefficients in a balanced chemical equation, but in a mass action expression, they're going to be represented as the exponents to their respective substance. And so overall, the equilibrium law can be defined as this, where the equilibrium constant Kc, to which, if you recall, is a ratio of the two rate constants, is equal to the concentration of the products raised to their own power, which in this case is going to be the coefficients. Divide this by the concentration of reactants raised once again to their own coefficient. Okay? And so this last part is going to represent the mass action expression. Where this part right here is going to represent the equilibrium constant Kc. All right, so let's go ahead and talk about Kc just a little bit more. So we know that the equilibrium constant Kc is simply the ratio of the two rate constants, the forward and the reverse. And so the value of the equilibrium constant is only affected by variables that affect the actual rate constants. So let's go ahead and look at our proof once again, or the result of our proof. The equilibrium constant is simply a ratio of the two rate constants, which is equal to the ratio of the products raised to their own power. Divide that by the concentration of the reactants raised to their own power. And so if you guys recall, through our derivation that the rate constant and the concentration came from the rate law. So let's go ahead and take a look at that real quick. And so according to the rate law of the forward reaction, if we change the concentration of the reactants, so for example, if the concentration is 1, and if we change that concentration to, for example, 2, then it will affect the rate of the forward reaction. However, changing the concentration does not change the rate constant for either the forward reaction or the reverse reaction. You're simply changing the concentration. And so therefore, changing the concentration of your substances will not affect Kc. Thus, does not affect the equilibrium constant Kc. However, the variable that will affect the equilibrium constant is temperature. And so this is the Arrhenius equation. And so typically the Arrhenius equation describes the rate constant as this capital A, this probability factor, raised to, multiplied by some exponential, which is raised to the activation energy over R and T. And so this variable, and this variable, they're all constants. Okay, so once you guys have figured out the activation energy for that specific chemical reaction, that would be the activation energy for that chemical reaction. However, it is the temperature that can be changed. And so therefore, temperature will affect the rate constant K, and thus affecting the equilibrium constant Kc. Okay. So one of the key points that you guys just have to keep in mind is that temperature will not only change the rate constant K, which is what we discussed in the chapter of kinetics, but can also affect the equilibrium constant Kc. And we'll take a look at that situation a little bit later in future lecture videos. So overall, capital Kc, or capital K subscript C, is used to represent the equilibrium constant for aqueous solution. There is another equilibrium constant for solutions that are gas phase, and we'll take a look at that in future lecture videos. And so overall, many students will probably enjoy this part. The value of Kc is unitless. And so remember how in first semester of general chemistry, you guys always have to write your units at the very end of your answer. But it turns out that Kc is unitless since it's a ratio of two rate constants. And so their units are going to cancel each other out. So for example, if the reaction is first order, then the unit for the rate constant K is going to be 1 per second. And so if we have a rate constant in the forward direction, the unit for the rate constant in the forward direction is 1 per second. And the unit for the rate constant that's going in reverse, just for argument's sake, will also be 1 per second if the reverse reaction is first order as well. And so notice how these two units are going to cancel. And so if you divide the two values, k forward over k reverse, that's going to give us the equilibrium constant kc. And this value is once again unitless. Okay, so please do not add in a unit when you calculate the value for kc. But you guys do need to write your units for the rate constant, little k. Another thing that I want to point out is that when you are writing the mass action expression for a chemical reaction that's at equilibrium, in other words, you're describing Kc, that means all of the concentration terms, whether it's reactant or product, must be at equilibrium. And so what do I mean by this? So if you recall, the equilibrium constant is equal to, for example, the concentration of, what was it again? F, G, D, and E. Okay, so let's go ahead and use that. So D and E will produce F and G. Oops. Okay. And so here, the concentration of F raised to the F power times this by the concentration of G raised to its coefficient divided by the concentration of D raised to its own coefficient times this by the concentration of E raised to its own coefficient. So that's going to give us the value for the equilibrium constant Kc. And so if you guys are trying to describe the system that's at equilibrium by using Kc, that means that each and every single one of these concentration terms must be at equilibrium. Okay, so EQ is my abbreviation for equilibrium. And so if these concentration values are not at equilibrium, then you guys are not calculating Kc. You guys are calculating something else, and we'll talk about that in a future lecture video. So let's go ahead and apply this concept to a couple of examples. So here we have a gaseous dinitrogen tetroxide decomposing into gaseous nitrogen dioxide. And so here we have 0.0350 moles of dinitrogen tetroxide that was allowed to decompose in a 1 liter flask. And it's allowed to reach equilibrium. So what is the equilibrium constant if at equilibrium the concentration of dinitrogen tetroxide is this value and nitrogen dioxide is this value? Okay, so let me go ahead and highlight the question in a different color just to contrast it from some of the values that this problem gave us. So overall, what is the equilibrium constant if at equilibrium we have this amount and we have this amount? So for us to determine the equilibrium constant Kc, we need to know the mass action expression. And the only way to know the mass action expression is by writing a balanced chemical equation. Okay, and so if we're able to figure out the balanced chemical equation, we can write the mass action expression, and then plug in the values to determine the equilibrium constant Kc. So that's going to be our method of action. So looking at the first sentence, it says gaseous dinitrogen tetroxide decomposes into nitrogen dioxide. Well, dinitrogen tetroxide is simply N2O4. And so here we have nitrogen dioxide, and then that's going to be NO2. So we have, let me zoom in here, we have N2O4 decomposing into NO2. And so if I try to balance the chemical equation, that's going to give us 2 moles of nitrogen dioxide for every 1 mole of dinitrogen tetroxide. So now that I have my balanced chemical equation, I'm going to go ahead and write my mass action expression, where Kc is equal to the concentration of the products raised to its coefficient. Okay, and so here let me do this in a different color. So I'm going to take this and plugging it in the numerator, and I'm going to take the coefficient and represent that as an exponent. And so that's going to be divided by the concentration of N2O4 raised to the first power. Now remember, this is, we're describing Kc, so all of this must be at equilibrium. So we can only use concentration terms that are at equilibrium. So only use concentration terms, or only use concentration that's at equilibrium. And so what are they? Well, here we have 0.0350 moles in 1 liter. And so if I divide both of these two, I can express that in terms of molarity. But is this a value at equilibrium? No. It says that this amount was first present, and then it was allowed to reach equilibrium. So it's not an equilibrium concentration. And so we're going to ignore this value completely. And so what is the equilibrium constant if at equilibrium the concentration is this amount and this amount? So this last sentence is describing that this value and this value are equilibrium concentrations. And so since dinitrogen tetroxide is in the denominator, I'm going to go ahead and place 0.0292 molar below. And I'm going to place this value in the numerator, because that's for nitrogen dioxide. So the equilibrium constant Kc is equal to, I already forgot the concentrations, so this is going to be 0.0116 raised to the second power. Divide that by 0.0292 raised to the first power. And so if I were to plug this into my calculator, let's see what I get. So I have 0.0116 squared. Divide this by 0.0292. And so to the correct number of sig figs, I have 4.61 times 10 to the negative 3. And so that is my value for my equilibrium constant, Kc. So notice how at the very end, I'm leaving my answer to be unitless. All right. I'm just going to put in a note here that says unitless. And so we basically used all of these, we basically used the last two concentration values because that was when the system was at equilibrium. So hopefully it now makes sense for what I wrote over here, that these concentration values must be at equilibrium for you to plug it into this mass action expression describing Kc. If it's not at equilibrium, then it's something else, and we'll talk about that in a future lecture video. All right, so let's go ahead and do one more problem. So here we have a chemical reaction, chemical equation that's already given to us. It's already balanced. And so let's see here. If the equilibrium constant Kc has a value of 4.62 at that specific temperature, and if the equilibrium concentration for SO3 is this amount, and the equilibrium concentration of O2 is this amount, what is the equilibrium concentration of SO2? And so in this example, the equilibrium constant is already given to us, and we're just trying to look for the equilibrium concentration of sulfur dioxide. And so for us to do this, we need to first write a mass action expression, and that mass action expression is going to be reflected from the balanced chemical equation. And so remember that the mass action expression, let me just zoom in, can be seen as a ratio of products over reactants raised to their coefficient. Okay. And so here in this case we have SO3 is our product, so we're going to write that first. So the concentration of SO3 raised to the second power, divide this by the concentration of SO2 raised to the second power, times this by the concentration of O2 raised to the first power. So once again, I'm getting these exponents from, this might be messy, the coefficients in the balanced chemical equation. And all of this will equal to the equilibrium constant Kc. So now that I have my mass action expression, I can go ahead and plug in these values that's given to us. And so it turns out that Kc is 4.62. So I'm going to put in 4.62 right here. And then that's going to equal to the concentration of SO3. That's at equilibrium already based on what the problem told us. So the concentration of SO3 is 0.254 molar, and it's going to be raised to the second power. And so what we're looking for is SO2, so that means that this term is not going to be substituted in by any values. And lastly, the concentration of O2 is going to be 0.00855 molar raised to the first power. Now remember, the brackets represents molarity, which is something that was covered in a previous lecture video, probably in kinetics. All right, and so all I'm going to do is just solve for SO2. So for me to do this, I'm going to go ahead and multiply this term to the other side. Okay. And what I get is 4.62 times this by 0.00855 equals to 0.254 squared over SO2 raised to the second power. All right, and so what I'm going to do now is I'm going to go ahead and multiply this to the other side, and then divide this whole term. So I'm basically switching places. And so, and you guys can actually solve this however way you want. I think I'm taking like an extra step here. I just want to show my work. And so here I have SO2 raised to the second power times this by all of this stuff, which equals all of this. All right. So now that I've moved my SO2 to the numerator, I'm going to go ahead and take this whole term and divide it. And so what I get is SO2 squared, which equals to 0.254 squared over 4.62 times this by 0.00855. All right, now I can go ahead and punch this stuff in my calculator. So I have 0.254 squared. Divide this by 4.62 times this by 0.00855. And then that's going to give me a value of 1.63. So we're just keeping 3 sig figs. And so to solve for SO2, remember that I have to get rid of this squared, and to get rid of a square, you have to square root it. So I'm going to go ahead and square root my answer. And so the value, the concentration of my SO2 at equilibrium is equal to 1.28 molar. So notice that I have to include my unit of molarity when I write my final answer. All right, so you guys have now been exposed to two ways of applying the mass action expression. You can basically solve for the equilibrium concentration of any substance if the value of Kc is given to you, or if it's not given to you, and if you have the equilibrium concentration for everything else, then you can just go ahead and write the mass action expression, plug it in. Make sure that you guys are only using concentrations that reflects the equilibrium values. All right, so that's pretty much it for this lecture video. I'll go ahead and see you guys in the next one. Bye.